This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome everyone to lecture number 10. And what we're going to do, whether you're ready or not, is have a look at how to implement this finite state machine. So the first thing you do when you want to implement it is that you start with a test bench. Why might it be a good idea to start with a test bench? I usually find, if I'm having to do something reasonably complicated, by starting with the test bench, then that forces you to think clearly about what your module actually does, what your design actually does. Because when you write the test bench, you have to work out what are the typical input signals that go into your doohickey and what sorts of outputs do you expect from it. So everyone's got their own way of doing it, their own style, but often it might be good if you start with the test bench rather than start with your design. The second reason it might be good to start with the test bench is that then you can build your design up. Start with something very basic that compiles. Whenever you do anything complicated, it is always a disaster. Well, it's not a disaster, it just takes more time doing it this way than another way. It takes more time to try to write the thing in one go. Because you write it in one go, you press the compile button, and for the next hour you're debugging a missing semicolon here, a wrong variable name there, etc., etc. It's always faster to grow your code. Start with something that works and grow it. Now if you have a test bench there, that's even better, because your test bench can call the module and you can start to grow it and start to pass some of the tests as you go along. That's for more complicated stuff anyway, but it never hurts to get into good habits right from the start. So here's my test bench code for, remember this is what we want to implement from last lecture. We want to implement this so we see that the input is going to be a sequence of bits and the output will be a 1 when we've detected either 4 zeros or 4 ones. So my test bench will instantiate the module we wish to write, a finite state machine. Because from now on pretty much everything we're doing is going to be synchronous sequential design, it means we'll have a clock there driving all our flip-flops. So you're going to be sick at writing this line here that generates a clock forever. The only trick when you write this line is to figure out when is the rising edge. So the way I've done it here, the rising edge is at odd times, 1, 3, 5, 7, 9, etc. And then down here, I just generate different inputs after different times and feed it in to, well, it automatically gets fed into my module here, and my monitor is monitoring the module. I am hoping that you will notice that rather than writing finish, I write stop, and that you're curious about that, and I'll give you two answers. Most of the time it doesn't matter. If you were using Model Sim directly, and I no longer teach that in this course because it's just yet another thing you need to learn, and it just seems easy to let you call it from quarters because you have to do that anyway. But if you use Model Sim directly, and if you end your code with finish, finish is a bit more powerful than stop. Stop will just stop it, everything will be nice in Model Sim. Finish, it goes, oh, you're finished, so it closes the waveform window and all the outputs and whatever, and it's not so nice. So for most purposes, it doesn't matter whether you write stop or finish. If you use Model Sim, stop is nicer. Does it really matter for this course? No. So here's my test bench. Any questions about my test bench for my finite state machine design? Should be fairly standard by now. I make sure, remember, the rising edge occurs at odd times, so you notice how I change my input at even times. Never change the input at the rising edge of a clock. We'll find out why later on. For now, just don't do it. So if you're not allowed to change the input at the rising edge, well, you could try to be sneaky and change it at 0.95 or something, but why be sneaky when you may as well just change it at the falling edge, whatever's easier. Any questions? Yes? Exactly what it sounds like. It will do that loop forever. It'll always do that loop, and it'll never stop.
And is this forever linked to the last stop, like control by the stop?
I'd like to say no, it's not linked in any way, but what you have is you've got your simulator that works in parallel. So your forever loop, that's one friend handling it, and he goes on forever. That initial block down here, that's another friend doing that, and when that friend says stop, that stop, it's got a dollar sign there. That's for the whole simulator. So that stops the whole simulator. So the stop stops everything. So in your mind the answer might be yes, they're linked, but in my mind they're not linked. But when you get to that stop, it stops everything because it stops the simulator. So that forever will go on forever, but of course when you switch off your computer it stops, right? So that stop switches off the simulator. So if something's going forever, it keeps going forever until you pull the power out. That's what the stop does. Any other questions? Okay. Yeah? When will your computer stop? When you pull the power out. That stop switches off the simulator. That forever will go on forever while the simulator is still alive. So it's like my computer. I can start up a word processor and I never shut it down, but when I shut down my whole computer, it stops. Any other questions? Okay. So the second, now of course when we're doing very trivial things at the start of the course, it doesn't matter how you do it, you can do it all at once or whatever, but for anything more complicated, start with a skeleton. And the most basic skeleton is just the declaration of the module with nothing in there. So I've written my test bench. The next thing I do is write my skeleton code here with just the correct inputs and then module, and I hit the compile button. Not the full compile button, because then I'll be there forever, but I just make sure I haven't made a spelling mistake or typo or whatever. The next thing we do, so this is a standard procedure for going from a state diagram to implementing it in Verilog. That's what I'm teaching you now. Now it only works for state diagrams that you can draw in a finite size, but that's all we're doing for the moment, okay? And the concept is the same in general, it's just you need to learn a few more things. So the first thing we need to do is we have to map our states. Our states, remember, you need to remember it because I don't think your eyesight's that good. Our states are A, B, C, D, E, F, G, H and I. There is no A, B, C, D in the FPGA. In the FPGA there are only flip-flops. Each flip-flop can store a 0 or a 1. You get a bunch of flip-flops and you can store a bunch of 0s and 1s. A bunch of 0s and 1s can represent a number. 8 flip-flops can represent a number between 0 and 255. So we assign to each state a number. How do we assign the number? You can assign it any way you like. What is the effect of changing how we assign a number to a state? The design will work no matter what, but some assignments might prove to be faster. You can clock it at a faster rate than others. And some assignments might reduce the amount of logic you need. So a bit later in the course we'll talk about how changing this assignment can tweak the design. Do you want it a fast design? Do you want to use a small number of components? Because remember, an FPGA costs more money the more logic elements there are. And while you mightn't care for your home burglar alarm, if you're making 1 million products, you'd rather save 5 cents a product by squeezing your design into a smaller FPGA than being able to run it at a gigahertz when you only need to run it at 50 megahertz. So depending on the design, you might want to tweak its performance. So we can tweak the performance by changing how we assign numbers to states. In fact, Verilog can do that for us because what am I talking about? Quartus can do that for us because Quartus actually understands finite state machines. If you write your finite state machine the way I'm teaching you today, Quartus will recognize that and it can change your state encoding for you to try to optimize it. These are all advanced things. Right now, I'm just saying assign a different number to each state, full stop. That's all you need to do. So, the simplest way of doing that is simply using the numbers 0, 1, 2, 3, 4, 5, 6, 7 and 8 in this case. And I explicitly make this assignment by using local param. If you know your C code, that's a local param is a bit like me saying const int Fred equals to 23. And that is better than doing a hash define in C because this way the compiler knows that Fred is an integer and it can type check that for me. So that's roughly what's going on here. So I assign a unique number to each state. If you don't know how to do that, then I recommend 0, 1, 2, 3, 4, 5, 6, 7 up to the maximum number of states you have. Once you understand what's going on, you'll see how you can do some clever things by changing this around, but for now this will be fine. Any questions? Okay. Yep.
Why is this A equal to 4D0 and not 4B?
So D for decimal, and I want to count, and although I could count in binary or hexadecimal, I'm used to counting in binary, decimal, and so I use D for decimal, and so I just write 0 to 8 here.
So that is like from 0 to 8, but this in decimal values, not in bits like H1, H2, H3.
Correct, so A is the number 0, B is the number 1, I is the number 8. Because later, well, over here, well, that's my next question to you. So I'll answer your question, but first I'll ask all of your question. If I've decided to use the numbers 0 to 8, how many flip-flops do I need to be able to store a number between 0 to 8? Can I do it with one flip-flop? 2, 3, 4? I need 4 flip-flops. So that's why each of these numbers I've declared to be 4 bits wide. To let the Quartus know, well, to help Quartus error check that I will be using 4 bits for my flip-flop. It would work without me putting 4 there, but I get a warning from the compiler because when I assigned a flip-flop to the value A or B or C, it'll go, well, I've only got 4 flip-flops, and you're asking me to assign a 32-bit number to it or whatever, I'm truncating it, it'll do that, but it'll give me a warning. So often in Verilog code, people are very precise about how many bits wide each number is. Very good. So at this early stage, if you ever get confused, it's probably, although I think a bit differently, but it's probably fine to think every number you see, just think that Verilog's going to convert it to binary, and I don't think you'll go wrong with that. So even though I wrote it in decimal, just think that will be converted to binary, and that's how it's dealt with. In your FPGA, there are only bits flying around. There's no such thing as decimal numbers in your FPGA, so to speak. As you should know from your workshop 1, where all this was covered, the number in front says how many bits I have. As you may or may not have figured out by now, if I do this assignment here, so on the right-hand side I have got a 4-bit number, 0011, And on the left-hand side, I have got a register which is 8 bits. So what happens when you try to put a 4-bit number into an 8-bit register? Well, what happens is it gets what's known as sign extended. Now, I haven't taught you about negative numbers yet. You can actually represent negative numbers in Verilog. But if we just but luckily this x cannot be a signed number. You might remember, if you're very good, that in workshop 1 there was a hint saying that I could add an optional s in here to make it a signed number. But when we don't do that, they're all unsigned, which means they're just positive. So because everything's positive here, all that happens is when you have to extend it to get more bits, you just set them all equal to 0. If it were signed, then if the leading digit was a 1, that 1 would get extended here and it would all work, but you don't need to know that yet. So for the moment, if you're extending a number, you need more bits, you just put zeros there. And conversely, if you've got an 8-bit number and you're trying to put it into a 4-bit register, it's the least significant bits that end up in there. The most significant bits get truncated. So there are rules for when you change the number of bits. A lot of Verilog compilers will often give you a warning when you change the number of bits, just so that you can double check that you really want to do that. Any questions there? So I'll leave this test for you to do, because you can easily check your answer by using an online Verilog simulator. Okay, so what have we done? What are we doing? We're trying to implement a finite state machine given the state diagram. And the first thing we have done is we have assigned numbers to states, and we have declared that explicitly using a local param statement. The next thing we do is we declare our flip-flops. And I do that, and why has my cursor disappeared? Because it's a Microsoft thing. The code in red declares my flip-flops. I need 4 flip-flops, and that's what happens with my reg 30 state. That state is going to become a flip-flop. Remember, it's not the reg that makes the flip-flop. What makes the flip-flop is the always at pos edge clock. That always at pos edge clock says whatever's inside here only happens at the rising edge of a clock, and the only time state changes is inside there. That is what makes state into 4 flip-flops. That and the fact that state is 4 bits wide. A finite state machine needs to start somewhere, and it's very important you specify where it starts. So you notice I have initialized state to A. Think about that for a moment. It's not a C programming language where it just sets the variable state to A when it runs that code. No. This state becomes 4 flip-flops in the FPGA. Every time you power up the board, somehow magically, those 4 flip-flops are going to start initialized to whatever number A represents. So part of configuring the FPGA is configuring the initial state of all the flip-flops inside there. So remember when you configure, so when you press the programming thing and start or whatever, that sends a bunch of numbers to the FPGA. Those numbers configure all the lookup tables, they configure all the routing in there, and they configure the initial conditions of all the flip-flops. So when you start the board, all the flip-flops are in a known state. If you don't initialize it, then the default initialization is 0 for Quartus. For Model Sim, the default initialization is what? X for don't care. And so you get problems with a mismatch here if your design relied on that initialization. The next state, if you recall our diagram of a finite state machine, you have a flip-flop here. Its output is the current state. The current state gets fed back through some logic to form the next state. And it's the next state that gets clocked into the flip-flop at the next rising edge. So therefore, my flip-flop circuit is complete by saying that at every rising edge, the next state gets photographed and becomes the new state. It is up to us to write some logic defining next state. You may well ask, why have I declared next state using a reg? Well, maybe I just need to declare it to be a wire, okay? I know that coming up I'm going to use a case statement to implement my transition logic, also known as next state logic. So my next state is a combinational function. Whether it's a wire or a reg just depends on how I write it in Verilog. If I write it using an assign statement, it will be a wire. I'm probably going to use a case statement, so I made it a reg. So it's a reg for a different reason than state. So state's the actual flip-flop. Next state is the output of combinational logic telling me what my next state will be. So this code here is pretty constant. You can do this basically without thinking, because it's the same every time. Sorry, I have a technical issue here with this thing. Okay, we're back again. The next thing we do is the output logic. So in this course we primarily focus on more finite state machines, not as in lots of, but not merely, but more, the name, more. And a more finite state machine, the output is a direct function of the current state only. Now I often get into trouble because I somehow like to say the output only depends on the current state, but that's actually a bit misleading because of course the input influences the current state, and if the output depends on the current state, the input therefore influences the output. So if you ever read something with that words in there, I explain. So I'm now trying to get into the habit of saying the output is a function of the current state. And that's why we can write the output logic already. And, oops, how did that happen? And we look at this design here, and I ask, well, when is the output a 1? And the output's a 1 if I'm in state E or if I'm in state I. In this design, it's not as if half the time the output's a 0, half the time's a 1 or whatever. The propensity is that the output's normally a 0. So knowing that, I choose a simple way of defining the output logic. I say the output is a 1 if and only if I'm in state E or I'm in state I. Now, I don't have to use an assign statement for the output logic. I could have used a case statement, but I used a bit of a human thinking, so to speak, and you look at this and go, oh yeah, this is an easy way of representing the output logic in this case here. The key point is the output logic will always be combinational logic. That's what we talked about first in this course. And it's fully defined by a truth table. Yep.
You haven't visualized it, so how do you know its output will be 0 when it's not state B or I?
So two things. So firstly, remember up here I have initialized my initial state to be state A. So when I first turn it on, I'm definitely in state A. Yeah, otherwise I could be in a random state and I'd be a bit worried there. Any other questions? So if you're good at C programming, that line should make perfect sense. In C programming, 0 is false, everything else is true. Here I just have one bit, so 0 is false, 1 is true. So is state equal to E? 0 for no, 1 for yes. And so state equals to E, I get 0 or 1, state equals I get 0 or 1, then I OR them together, so that works. So you can get used to that idiom there. Any other questions before I emphasize that this is just implementing a truth table on the next slide? Okay. So I just want to emphasize, although I chose to write it that way, you could have written it any other way you like, because it is simply combinational logic. You write down a truth table, you write down the state here, and you write out the value of the output here. That's a truth table. And you just have to implement that truth table. You can always do that using a case statement. You might find a case X is faster, you might find an assigned thing that I did is faster, you might find some if statements are faster, but that's a human thing for how you would like to do it. It is just a combinational circuit that you need to implement there. And the same thing happens with the transition logic. The transition logic is just a combinational circuit, fully defined by its truth table. So all you need to do, in principle, is write down the truth table and then implement that using a case statement. That will always work. If your truth table is huge, you might not take that approach for practical reasons, but that will always work. And that's the first thing you should learn how to do. So in this case here, I was a little bit sneaky. If I'd done it the full way, my truth table would have to contain both my current state and the input. And so my case statement would have been case, squiggly bracket, state, comma, and whatever I call the input, W or whatever. But I chose not to have a full case statement because the input was only 1 bit and I knew that I could do it this clever way. So I'm being a little bit clever here in doing it this way. But this is, again, an idiom that you should be familiar with. So all this says is, because remember the next state depends on the current state and the current input. And I can write down the rule any way I like. In this way, how does it work? Well, let's say my current state is C and my current input is 0. So my current state being C, I come down here, my next state is my current input a 0 or a 1? Well, it's a 0. So that means that I then move on to state D. Because this is an inline if statement. If W is true, it returns F. If W is false, it returns D. If W is 0, that means W is false, because 0 is the same as false. Remember your C programming. And so if I'm in state C and the input's 0, then I move to state D. And hopefully, luckily, that's what this diagram is telling me to do. I always have a default statement down here, sending me back to the initial state, because I've got 4 flip-flops. So those flip-flops can represent a number between 0 to 15, but I only have 9 states, a number 0 to 8. So if a cosmic ray, and they do exist, hits one of my flip-flops and changes the bit in there, I might jump to state 12. State 12 doesn't exist. What do I do? Well, it's better to do something. You may as well go back to the initial state. Not only is it better to do something, but if I didn't have that, Quartus will see that there are some conditions which are not covered by this case statement, and it will give you a rude message about inferred latches and get really cranky. So for both reasons, put in the default statement there. Unless, of course, your finite state machine has only got 8 states, and so only if you're using all the possible combinations of the flip-flop outputs can you not have that default statement there. Otherwise, you've got the default statement there. Any questions at this point in time? So it's a standard procedure. Once you've got the state diagram, you assign numbers to states, you write the code I showed you with the local param, your state, your next state, you're always at pos edge clock. Then you've got two logic blocks to do, the output logic, and that is just a truth table. Given the state, you know what the output is. That's a truth table. You implemented this combinational logic. And then you do your transition logic. And again, that's a truth table. Given your state and your input, you can work out what the next state is. That's a truth table. And then you're done. You're finished. You've got your design there. And that's it. The only room for human creativity is how you choose to implement these two combinational logic blocks. How do I implement the output logic? How do I physically write down the transition logic? It will always work with a case statement, but there might be nicer ways of doing it or faster ways. That's the only place where human judgment comes into this, at this level of the exercise. Any questions? The other, I much prefer creativity, but sometimes creativity is bad because A, someone else might have to read your code, B, Quartus needs to read your code, and if you do it this way, it recognises it's a finite state machine and can optimise the implementation, etc. I'm emphasising again that everything's a truth table there. Then I can simulate it. And so the top one's my clock. And remember, exciting things only happen at the rising edge of the clock. That's when the flip-flops change. Here's my input. Remember what this design's supposed to do. It's trying to detect when I have 4 zeros or 4 ones at the input. This line over here, how many ones do I have? Well, we have to count how many rising edges there are, because that's when you sample the input. So there's a 1 here, there's a 1 here, and there's a 1 here. Then there's a 0 here. So this represents 3 ones, followed by 2 zeros, followed by 1, 2, 3, 4 ones. And that's why I get a blip at the output, because it detected 4 ones. So make sure you understand how to read the output of this thing and check that it really is doing what that finite state machine is supposed to be doing. Any questions? Very good. Looking at the RTL view, we suddenly see something new, not a yellow canary, but a finite state machine in yellow. Because we followed these basic coding guidelines, Quartus recognised we were coding up a finite state machine and drew it as a block here with W as the input, and it even understood my local param and called the outputs E and I. That's pretty cool, actually. Pretty cool. But it sort of furthers my claim that everything's a finite state machine. So I'm teaching you what everyone else is doing. I'm not making things up because I'm academic. This is how the real world works. This is my output logic over here. My mouse has disappeared again. The Z thing, the OR gate's my output logic. And indeed, the output is a 1 if and only if I'm in state E or state I. And that's how you implement it digitally. It is a combinational logic circuit, as I was telling you it was. If you then double-click this yellow canary, you'll see inside it. And you'll see that here's the state diagram. Maybe not as pretty as what we had. Because we're humans and we knew what it was doing, we had the 0 inputs down here and the 1 inputs down here, etc. But this is the equivalent diagram. It's telling you the possible transitions. It tells you everything. It can show you graphically the state diagram. Okay, so if you like, that's the end of part 1 today. So I tried to show you how, given a state diagram, you can turn the handle and implement it in Verilog. Any questions about how to do that? Very good. So we move on to part 2. And remember, there was one place where we could use, where we could change our design, and that was how we assigned numbers to states. So one obvious way is just to use 0, 1, 2, which is what I did. I don't know why it's not liking me. So I could use 0, 1, 2 like I did. Another popular choice is to use what's known as one-hot encoding. One-hot encoding means that I'm going to have a bunch of bits, but only one of them is going to be a 1 and the rest a 0. That's the rule here. And so if I use one-hot encoding, that means each of my states is going to be represented by a binary number, only one of whose bits is a 1 and all the other bits are going to be 0. It's easy to just show you by pointing than trying to explain it in English. So, because I've got 9 states, I have got 9 bits. And state A is just all zeros, then a 1. State B is all zeros, then 1, 0. State C is all zeros, then 1, 0, 0. Hopefully you get the picture. Easier to just point my finger than to try to explain in English. That's one-hot encoding. It is inefficient in terms of the number of flip-flops I use. If I have got 16 states, and I number them 0 to 15, I only need 4 flip-flops. If I use one-hot encoding, I need 16 flip-flops. So it's inefficient in the number of flip-flops I use, but there's a benefit I get. The benefit is often the transition logic is very simple, and the design can run faster, a lot faster than the other design. So if you don't care about how many flip-flops you use because you're feeling rich and you just want a fast design, this might be for you. I can't guarantee this is the fastest. That's a deep mathematical exercise, but there's a good chance that this will be faster than just the usual encoding. So I'm not going to go through this in great detail because I just want you to understand the concept. The concept's more important than being able to do it. But if we think about it, what happens when we change the state encoding? We change the number of flip-flops we need, but we also change the transition logic and the output logic. Because when you write down your truth table, remember you've got the current state here and the next state here. And how you represent that changes how the table looks. And even if it's a great big table, you can imagine that some truth tables only require a few logic gates to implement, while others require a lot of logic gates to implement. I'm not going to talk about computational complexity or anything in this course, but you can hopefully appreciate that if you change the state encoding, you change the complexity. It's hard to predict how you change it. The fact is, it changes. Therefore, there might be an optimum state encoding for any given problem. That's for you to worry about in a more advanced course. I'm just showing you there's the possibility there of changing the performance of the design, etc. Any questions there? You just have to appreciate that changing this can change the behaviour. And that's about it. And remember that one-hot encoding will usually give you a faster design, but it's not guaranteed to do so. Okay. So your homework's to read and understand chapter 14, and hopefully it just reinforces what I discussed. I've told you the story my own way. The book will tell it in a different way, but it's the same story. Okay, so some good news is that in some sense we're now at cruising altitude. I warned you the start of this course will go very quickly and you had lots to learn, but I think the worst of it is now over. And so that means I can actually slow down a little bit. I had to go quickly because We have got a fixed lab timetable. I can't slow that one down. And to appreciate some of the things we're going to talk about later in the course, you need to understand Verilog. You need to be comfortable with it. So there was a big push at the start of this course to get you to use Verilog, to use Quartus, to use Model Sim, etc., so that all the other things I want to talk about make some sense. But we're now there, which is good news. So I'm going to revisit previous topics and tell you more about what we went through quickly, and we're also going to cover a few more topics. And then the rest of these slides, I'm actually not going to go through them. I'm happy for you to leave early. I've just tried to summarise for you what the first few lectures were. But I will answer any questions you have about the course or about today's lecture now before we finish. So, any questions? Yeah. Sorry? Oh yeah, yep. Yes. So the question relates to when you'd extend, so this is more of an advanced thing. If I have got a 4-bit number that I'm then trying to put into a longer one, if I do this is equal to this, then what happens is that that number gets copied into these bits, and then normally the leading bits are just set to 0. For everything we're doing, that's what we want. But a bit later, we're going to learn about signed numbers. And the number representation is often key to how humans think. And so what we want is that if this number here represents, for example, -3, then when I put it into this 8-bit register, I also want it to represent -3. So I should have pointed out, it was remiss of me, this idea of extending it by zeros has the key property that if I've got the number 4 in here, then when I extend it to 8 bits, I still want to be representing the number 4. That's why I had zeros at the front, to keep that key property. I want to preserve that property if I work with negative numbers. So if -3 is in this 4-bit number, then I want -3 to be in this 8-bit number after the assignment. And when we learn about 2's complement, we learn that basically the leading bit is a 1 if it's a negative, and the way to get this one to be a -3 is to have these all 1 for a different reason. So that's why extending, you basically look at what this bit is and you extend that to the left, and that magically works with 2's complement arithmetic, so that whatever number is represented using 4 bits, the same number will be represented by 8 bits. And I should have explained that from the start. Maybe I'll do in a later lecture. But that's why you either have 0 being extended or 1 being extended. Any other questions? Yep.
For the finite state machines, if you want the output to be like a display,
Yep.
could you output more than just 1 0? Could you output like a 8-bit number, for example?
Sure. The finite state machine, you can have however many bits you like as output. So when you start doing that, that's when writing the output logic will become harder, because you wouldn't just use a single assign statement because it will become too complicated. But that's a Verilog question as opposed to a technical question. Yep.
I'm going to be asked to simulate the transient effect by the
So I simulate the transient effect of...
the transient effect with
Yeah, in the labs you will. So by changing from the cyclone 5 to the cyclone 4, you can actually see the time delays in the components and see the transient response, etc. So you'll get to see that. Sorry? Yeah, you have to know everything for that. Now, as I said in the email, on the one hand you need to know everything, but my focus is on what's the most important things to know. So if you've seen something time and again, chances are you should know that. If you want to get 10 out of 10, then maybe you need to be able to do those trickier things. Any other questions? Okay, we'll stop the lecture here, but I'm still around if you want to ask me questions individually.